Or to the cloud. All right, we are ready. So if you take a look here, I have these printed out for you. So we're going to learn about these different segments in a triangle. All right, so the first one, let's draw it first and then we will define this. So let me get a whole bunch of different colors so I'm ready. So to draw a median, you are going to start at any vertex you like, it doesn't matter. I'll just start at the top one. And you're going to draw a line segment that goes to the midpoint of the opposite side. So I'm going to eyeball about where the midpoint is. And I'm just going to draw this line. I'm going to mark these two sides congruent. Because if it doesn't go to the midpoint, it's not a median. So that's what we're looking for to have a median. It is a segment from a vertex to the midpoint, has to be the midpoint. Okay. Oh gosh, thank you. Midpoint of the opposite side. Okay, so that's what we need to have a median. Up next is our friend, the altitude. When you think of the word altitude, what do you think of? Yeah, so a lot of times we talk about altitude of like a plane. So, and that's literally just how high the plane is above the ground, right? That would be its altitude. So altitude is kind of another word for height. Now, when you measure height, when you go to the doctor's office, let's pretend, and you go and you stand up there and they measure your height, sometimes they flop that thingy down, right? Aren't you standing up perfectly straight or as straight as you possibly can? You are perpendicular to the ground, aren't you? Whoever went to the doctor's office, they said stand up for your height and you went like this. You don't do that, right? You stand perfectly straight so that you are perpendicular to the ground. That's exactly what an altitude needs to be in a triangle. It's got to be a segment. It can, again, start at any vertex. It doesn't have to be the top one. But if I start at whichever one I'm going to start at, I have to drop perpendicularly to the opposite side. So if I do that, it's going to drop straight down and I have to know that it's perpendicular. So it has to be marked as such. Okay, so a segment, oops, starting or from a vertex that drops perpendicularly to the opposite side. That's what we need. Okay, perpendicular bisector is one of my favorites because it literally tells you what it's doing. The name tells you. We've talked about perpendicular bisectors before. So in a triangle, it's just perpendicularly bisecting one of the three sides. It doesn't even matter which side. So let me pick a different color here. How about orange? What a festive fall color. So what I'm going to do for the bottom, I'm going to eyeball where the middle is because I need to bisect that side. And I also need to be perpendicular to it. So you'll often see the perpendicular bisector drawn as a line, but it doesn't have to be. It could just be a segment that stays, like it doesn't have to keep going outside of the triangle. It could have stopped right there, but no, this one does not have to be from a vertex. In fact, it's one of two in this list that does not have to start at a vertex. Could it ever start at a vertex? Could you imagine a scenario where this thing does hit a vertex? Sure, the isosceles triangles, right? So it can hit a vertex, but it doesn't have to. So is perpendicular to a side at its midpoint. So we'll even add does not necessarily, I spelled that wrong. Is that, you know what the word I'm trying to say. I don't know if I spelled it right. Does not necessarily hit a vertex. I'll add a double one, but it can. Angle bisector, this is another one I know you know. We've talked about angle bisectors already. So this one obviously has to start at a vertex because that's the only way I'm going to bisect an angle. And it's just going to, I'm just going to try and eyeball as best I can. I want to just split that angle into half. So an angle bisector would look something like that. Again, it could start at any vertex, it doesn't matter. It just has to bisect that angle or wherever it's coming from. So an angle bisector bisects an angle of the triangle. Okay, that one we know about. And then the last one is our friend, the midsegment. So a midsegment, what color have I not used yet? Pink. See how that shows up. Oh, maybe I should use red. Let's show it better. So a midsegment is going to be a segment that joins the midpoints of any two sides. So I'm going to eyeball the midpoint of this side, and I'll mark it as the midpoint. I'm going to eyeball the midpoint of this side. So when you connect those two dots, those two midpoints, that is what you have just created, is a midsegment right there. Okay, so a segment that connects the midpoints of two sides. Cool. So now we have those, and I want to stress to you, there's going to be, it's definitely on your test, but let me see if it's on your quiz. Don't think it's on. Yes, okay, your chapter quiz at the end of the week. I'm going to give you a picture just like this, and I'm going to say, what is this thing? So if you need to make a flashcard, or I don't know, but for whatever reason, kids every year seem to not care about this section. I'm like, no, you're going to get all of those wrong. I don't want that to happen to you. So we're going to practice them, obviously, but I'm telling you right now, if I draw the picture, you should be able to tell me which of these things it is. Oh, let me ask you this question. Will the midsegment ever touch a vertex? It doesn't in my picture, but is there a scenario where it could touch a vertex? No, this one never will. So if you want to add, will never. Oh, I'm sorry, thank you. Will never touch a vertex. Okay, so that's those. There's so much really cool stuff that happens with these, but unfortunately, I don't know why, but in this course, we don't go into great detail on them. But God, I can't not tell you at least one little cool thing. Check this out. You're not gonna believe it. You can just watch. You don't have to do this too if you don't want. You take a triangle, any old triangle, doesn't really matter, any triangle. if you draw in, let's just focus on the cool thing about the medians. If you draw in all three medians, so remember, that goes from a vertex to a midpoint. So here's, I'll do my color. There's one median, right? If I draw, just keep drawing them. So if I draw in another one over here, eyeball the midpoint. Again, this is not going to be perfect because I'm literally eyeballing and hoping for the best. So if I connect these two, that's pretty good. And then I do the third one. So spin this around. I'm going to mark where I believe the midpoint is and then draw in that third line. Let's see, this midpoint be right there-ish. And then let me get another color. Connect these two. First of all, I don't know if you realize how cool it is. Oh, I forgot to mark these. Do you see what happened? All three of these lines met at the exact same point. First of all, that's wild, because if you have three lines, they don't all have to intersect each other at the exact same point. Cool thing number one that they do, and that will happen every single time, any triangle, doesn't matter. Doesn't even matter. What? Okay. Furthermore, if you were to, I don't know, let's say this was made out of wood or something, and I cut out this triangle, and I try to balance this triangle on the tip of my pen. If I put it on that point, it would bounce perfectly. I know. That's wild. Thing number two. That thing has a special name. It's called a, oh shoot, now I'm gonna forget it. Medians are the centroid. Centroid is the name of that cool point where they all meet. It's called a point of concurrency. Again, you don't have to know any of this. Extra information. Why we don't teach it to you, I don't know, because it's fascinating. Thing number 3 or 10, I don't even know what I'm up to. That's so cool about this. The centroid breaks each of these medians into two pieces, a short piece and a long piece. The short piece is exactly half the length of the long piece. What? I know. So if I told you this part was 10, this piece would be 5. And that's just the medians. I didn't even get to the other things yet. That's nuts. I know, right? Gosh, maybe we could start a triangle club so we have more time to delve into these things. Wouldn't that be fun? I'll sign you all up. Okay. Anyway, so there's medians. They're so cool. All right, there are a few things at the bottom here to talk about. All right, let's see if we can figure these out before I just tell you what goes in these blanks. So first of all, the distance from a point to a line. If I wanted you to measure, let's just say I have a line and I have a point that's not on that line. If I said, hey, how far is that point away from that line? How do you think you would measure that? How do you measure that distance? Anybody have a thought? If I asked you like, hey, how far are you away from the wall? What would be the best way to measure that? I don't mean like with what tool. I mean like, would you measure like to the corner? Would you measure? Yes, exactly. You would measure from you perpendicularly to the wall. So if I have a point that's not on the line, I just drop a perpendicular. Okay, so we always measure the distance from a point to a line as this distance. Okay, so that would be the distance we are looking for. All right, so how would we, distance from a point to a line is the perpendicular distance. So that kind of all goes together. There we go. All right, so there's that. Now we have a theorem. It says if a point is on the perpendicular bisector of a segment. Okay, so if you look over here at this diagram, we have a segment here And then I do have a perpendicular bisector. It's perpendicular at its midpoint. See how it's bisected? So they're saying, hey, if you pick any point on that perpendicular bisector, any point you want, it literally doesn't matter. I claim that something is going on between that point and the endpoints of the segment. What do you think might be true about those two segments I just drew, Carson?
They form an isosceles.
You're right, because they are equal to each other. So if you pick any point, so even if I had picked a point way down here, I claim, I'll do it in a different color. If you draw these from that dot to the endpoints of the segment that you bisected, my claim is that those two orange things are going to be the same. These two things I drew in pencil are going to be the same. Why? There's a really easy way that you can prove it. Really easy. Take a look at these two little triangles up here. Aren't these two little triangles? First of all, that's 90, this is 90, right? So they have an angle that matches. They also have a side that matches because that was given to me, right? Wouldn't they share this side down the middle? So wouldn't those two triangles be congruent by side angle side? So wouldn't these two sides be congruent by CPCTC? And couldn't I do that for literally any point on this? Like I did down here. I could do the exact same thing. I would have these two triangles be congruent. They also have 90s. They also share a side down the middle. So they also share a side angle side, CPCTC. So what we can say is if you have any point anywhere on the perpendicular bisector, then it is equidistant from the segment's endpoints. And now you can see the next one is basically just the converse of that. If a point is equidistant to the ends of a segment, then you're right there, sort of. Sounds like you are. The point has to be on the perpendicular bisector. Exactly. So if I have some random point and I know that it is equidistant from the ends of a segment, it has to be on the perpendicular bisector. Okay? Then the point is on the perpendicular bisector. Cool. So there's all the perpendicular bisector business. Now we're going to talk just for a moment about angle bisectors. So let's look here. If a point is on an angle bisector, then, okay, let's see what's going on. So I have in this diagram an angle bisector, right? We have a big angle, it got bisected. You can pick a random point on that angle bisector anywhere you want. It really doesn't matter. Pick one. Doesn't matter. You pick it wherever you want to pick it. Now, if I were to, remember up at the top here, we talked about finding the distance from a point to a line. That's what I'm going to do. I have a point, and then I have a line down here, the side of the angle, that point's not on. If I were to measure the distance from this point to this line, I'm going to drop a perpendicular. So drop the perpendicular as, as best you can. You want it to really actually look like it's a 90-degree angle. So I did that. And you could do the same thing to the other side, right? So from that same dot, I'm going to drop a perpendicular to this side. So there is the distance from a random point on the angle bisector to each of the angle sides. I claim that something is true about those two things. Let me put them in a different color so it's easier to talk about. This, can you tell that it's orange? No, of course not. I should have drawn them in there. So these two yellow things. Well, you can kind of see some yellow. I say something is true about those two things. What do you think it is? They are equal. And can you see See how I basically created two little triangles here? Wouldn't those two triangles be congruent to each other? Why? What method would you use to prove me that this triangle is congruent to this one? It has two angles marked, but we need more than that. Yes, they share a side between them. Angle, angle, side, angle, angle, side. So wouldn't that work no matter where I went? So if I put a point way out here, and I did the same thing, if I drop the perpendicular, and I drop the perpendicular over here, those two red things, same thing. I could now have two more triangles that are congruent to each other. So yes, these pieces end up being congruent. So that's the same as that. This piece would be the same as this piece, and you can keep going all day long. You can pick any point you want on the angle bisector. And it has to be equidistant to the sides of the angle. So if a point is on an angle bisector, then it is equidistant to the angle's sides. And then we can basically say the converse is also true. If a point is equidistant to the sides of an angle, then it is on the angle bisector. Does all of that make sense? How are we feeling? How do we feel about the segments at the top? I particularly like altitude. I feel like that one. Oh, well, let me ask you this. Who has to be perpendicular all the time? Out of those five, which ones have to be perpendicular? So if you don't see that little 90-degree angle box, it can't be that. Who has to be? Perpendicular bisector for sure, it's in the name, and the altitude. If you don't see that 90-degree angle box, it can't be either of those two. Who has to hit a midpoint? Carson?
Mid-segment.
The mid-segment does? Who else? Median and one more. Perpendicular bisector. Those three have to hit a midpoint. So if you don't have the sides marked with their little congruence marks, you can't say anything. All right, let me give you, I'm going to draw some real quick and you just tell me what they are. I'm going to try and trick you because some of them can be tricky. What would you say about, I'm going to draw a triangle and then I will see if this red marker works out well. What would that red segment be? If anything, it could be nothing. Does that fit any of our definitions? Yes, Taylor. It is an altitude. It is. It's possible that an altitude could actually be the same as the side of a triangle that happens to be a right triangle. Think about it. The definition said it has to start at a vertex and then drop perpendicularly to the other side. It does that. Wow. Okay, cool. Let me try another one. What if I gave you, I'm trying to give you tricky ones right now. So let's do, I guess the only other tricky one I could think of is this. Or maybe I'll ask you this question. Let's say you wanted to, that's a pretty wonky triangle, but it's fine. What would you do if you wanted to draw an altitude and you wanted to start at this vertex? How are you supposed to do that? The triangle's over there. I need to go perpendicular to the other side. Any thoughts? You can't make it not perpendicular, right? I can't just like draw it sideways and like mark it with a 90 and hope that no one notices, right? I have to draw perpendicular. So here's what we do. If you have this only happens in the obtuse triangles like this. We literally can just take this by, because this is really a line, right? So if I just extend this line, usually we use a dotted line, but it doesn't really matter. Now you can see, oh yeah, I can drop a perpendicular to that. It would just be outside of the triangle. That can happen. It just happened. How about that? So altitudes can occur out completely outside of the triangle. Weird. I know. Okay. What would this one be? Let's do this. What is that thing right now? Julia? It is a median. What is it if I do this? Isabella? It's a perpendicular bisector. So does that mean that a median and a perpendicular bisector could sometimes be the same thing? Sure. As long as it has both of these markings, now it's a perpendicular bisector and a median, right? It's both. Could it be anything else? Julia? It is still an altitude. What? It's starting at a vertex and it's dropping perpendicularly to the other side. So you could also say altitude for that thing. Is this thing an angle bisector? How do you know?
Because it's an isosceles triangle.
How do you know?
That's the two base angles are congruent.
How do you know? These two? I mean, you're not wrong, but they're not marked. So how do you know that? Julia? You do have those two smaller triangles in here congruent by side angle side, right? If that's 90, that's 90, obviously. And they certainly share this red side. So these two triangles, you can get congruent by side angle side. Therefore, you're right, the base angles would be congruent. You could say it's isosceles. You can also say, well, CPCTC gets me those two angles. So, oh my gosh, you mean to tell me that if I have essentially an isosceles triangle and I draw one of these segments from the vertex angle, it has to be from the vertex angle. It's basically all of them. It's a median. It's a perpendicular bisector. It's an altitude. It's a, I forget what I'm missing, but what is it not? There's one thing that it's not. It's not a mid-segment. Mid-segment's sort of like this, that one's always kind of like the odd one out. Okay, not a mid-segment, but it's all of the other things. That's so crazy. Oh, I'm with you. The world of triangles. Who knew there was so much that we could literally start a club? Oh my gosh. What if I served high C? You would come, right? I know you would. Who wouldn't? Who would pass up that opportunity? Oh, pizza. Oh, I see. Anyway, so that is it for 4-7. Does anybody have any questions right now? What was that? No questions? No? No? Okay. All right. So I'm going to give you your homework. You have a quiz, which is why this homework I think I'm going to do a little bit of 4-7 and then a little bit of proof practice. So you have a little bit of both. Let's do that. So let's see. Oh, sure. I don't think it'll help you tomorrow, but I mean, if you find a way. Okay, so let me find a good proof practice here. That will help you on your way tomorrow. I think we did that one. Those ones. Those look good. I don't think we did those. Okay, yeah, let's do this. It'll be relatively short. So we'll do on page 155. I have you just doing numbers 1 through 6. And then for just 2 problems to do a little proof practice, page 144. I don't think we've done 3 and 4 yet. If we have, let me know. So here is the homework assignment. I have markings in my book, but I'm almost positive they're old, so I assume we have not done those 2. All right, I will go put this on Jupyter. Yeah, sure, just leave me your phone in the box, please. Did I even take attendance today? I did. I feel like it. I don't know. I'll check again. If anybody wants some index cards to make flashcards for your segment in a triangle, I've got plenty. Just let me know. Maybe I'll even set them out. I might even have different colored ones. I can't remember now. I will look in just a moment. I will check these notes where they belong. So I know that I have them next. Never actually do this again. Post these notes also. doing? Questions so far? Oh, the keg you're done? Sam, you're done?
I just decided I'm gonna wait till tonight so I can remember that.
Oh, golly.
I do it now, just to be like, 'cause I didn't